You just opened
Right.
your screen and then you just closed.
Okay. All right. Let's get started then. So first topic is kinematics, right? So what you do is to derive the kinematic equations, you assume that what you're seeking is, holy shit, this is really boxy. Can I use a smaller brush size? Let's see, size. Sorry, this is like the first time I used MS Paint. All right, whatever. You're just gonna have to deal with it. Sorry. Yeah, f of t, right? This is your function of position. If you want, you can write it as x of t, right? This is simply, you assume it can be written as a power series going from n equals 0 to infinity of some, again, a power series, right? So Cn times t to the n, not x. T to the n, all right? And you have to assume certain things about how the motion of the particle behaves, right? So for example, f at time 0 is what? Initial velocity, right? F of 0 is, again, initial position. So 0 equals xi. I hope you can understand what I'm writing.
Yes.
And then f double prime, yeah. All right, that's good then. F double prime of 0, and we'll stop here, equals a, right? And we'll assume all subsequent derivatives are identically 0, right? That's the reason why I didn't write initial acceleration, because we're assuming that acceleration is constant for all t. Right, so this equals 0, and so on. Right. Oh, by the way, feel free to, I can't really see, obviously, but feel free to just have push to talk on, and if you have questions, just ask in the middle. Yeah. All right. So then we can take the derivatives of this power series, right? But the first thing you want to do is you want to realize, okay, f triple prime, let's see. Actually, yeah, let's just take the first derivative of the power series, right? So you know f prime of 0 is, for example, f of 0 is xi, right? So just plug in t equals 0 into this, right? So you get f of 0, sorry, xi, initial position, which is equal to the sum going from n equals 0 to infinity of Cn t to the n, right? Or rather, since we're plugging in 0, we can immediately say t to the, or 0. That's a little bit tricky. Basically, we know this, right? We know f of t is equal to this, right? So you can write out the first, this is evaluated, this entire series is evaluated at t equals 0.
And the first term in the sum starts with 0, so wouldn't it start with like something times 0 to the 0th power?
Yeah, it would be 0 to the 0, but this would actually be, because it's just a shorthand for a series, so it wouldn't actually be 0 to the 0. What it would be is it would be C0 t to the 0, right? And t to the 0 is 1, so this immediately simplifies. You don't even have to do 0 to the 0, right? And then the rest is dependence, right? So it's C0 times t to the 0, or 1. C1 times t to the 1. C2 times t squared, or t to the 2, and so on forever, right? But the problem is all the rest of these terms have t dependence, right? So they'll immediately go to 0 when you plug in t equals 0, right? 0. And then you get that f of 0 equals xi equals C0, right? So now you know C0 equals x. That's simple. Now we know that f of t is, it starts with xi times t to the 0, or 1, plus the sum running from n equals 1 to infinity of the rest of the terms, Cn t to the n. T to the n, right? Now, we have this, we can take its first derivative and continue to plug in these terms. So you take the first derivative, you get that xi drops out because it's simply constant. I'm doing all these steps at once, by the way. I'm taking the derivative and plugging in 0. So you get, well, first of all, take the derivative here, right? This whole thing, I'm going to take the derivative inside and then evaluate it at 0 on the outside. So the derivative of xi is 0. The derivative of this sum is simply n minus 1 times cn tn. Or sorry, this is, yeah, that's right. This is incorrect. Sorry, this was rather it should be sum running from n equals 1 to infinity of right, power hops down, you subtract 1, right? So n times cn to the t times t to the n minus 1, right? Once again, we can write out the first term as 1 times c 1, right? So 1 times t to the 0, which is 1, plus other terms, basically other junk with t dependence, right? You plug in 0, once again, you arrive at the fact that f prime of 0 equals c1, and we define the first derivative of our position function. We defined it to be the initial velocity, right? So c1 is once again vi, right? So now we know.
Can you just repeat the last step? I started not being able to read it. So I wasn't okay. So I get where you just took the derivative of the power series, right? After that, what did you do?
After that, I simply plugged in 1, right? And plugged in 0 for t, right? So the first term becomes, it's ncn to the t times t to the n minus 1, right? So you plug in 1, or by the way, this entire thing is evaluated at t, right? So you have 1 times c1 times t to the 1 minus 1, which is t to the 0, which is 1. And then technically this is, again, all evaluated at t equals 0, right?
Yeah.
Now the rest of these are just polynomials in t, right? So the next one will be t to the first power, the next one will be t squared. And no matter what they are, when you plug in t, all the rest of these terms go to 0. The only term that's left is c1, right? And therefore c1 must equal vi. I hope you can follow that.
Yeah, that makes sense.
It's simply, if you've done Taylor series, it's very similar to that idea. Yeah. So f double prime of 0, once again, we know it. You can write this as, hang on. I'm going to clear. Right, I'm just going to scroll down, see if we have more space here. All right. So now, once again, we have f double prime at 0 is equal to, well, we know the first term is xi. The second term is, remember, it's xi times t to the 0, right? So the next term is vi, which is, again, so this is c0 times t to the 0. This is c1 times t to the 1, right? So vi plus the remaining terms, which are running from n equals 2 to infinity. To infinity. We're taking the second derivative of this, cn t to the n. Then we're evaluating this whole thing at t equals 0. Double prime, evaluated at 0. So I'm packing a lot into this little phrase, this one line, but I hope you can follow. So the second derivative, right? Any polynomial with a degree less than the derivative you're taking goes to 0, right? So t to the 1, and you're taking a second derivative, that goes to 0. T to the 0, 0 is less than 2, so that also goes to 0. So all these terms go to 0. All the terms outside of the sum go to 0, right? Inside the derivative. And this is a pattern, right? So the second derivative will be n, then n minus 1, By the way, I'm just gonna omit the n equaling 2 to infinity from now on. I hope it's clear what I. This is just for speed. To the n minus 2. Right? This is the derivative. We've evaluated the derivative, and we want to evaluate this at t equals 0. Right? I hope you see where this came from. N hops down, it's t to the n minus 1, then n minus 1 hops down, and then you subtract 1, right?
Yeah.
Then we can set this equal to, or sorry, now we evaluate the series, right? So you plug in n equals 2, you get 2 times 2 minus 1 times C2 times t to the 2 minus 2 plus dot dot dot, and I hope the pattern is clear. The dot dot is because the rest of these terms have t dependence, right? Because this minus 2 is constant, but this power is increasing. Therefore, the next one will be t to the 3 minus 2, which has t dependence, right? So this again becomes 2 times 2 minus 1 is 1 times c2. T to the 2 minus 2 is 0. T to the 0 is is 1. So this is 2 times 1 plus stuff with t dependence, which now we're plugging in t equals 0, right? These are all polynomials with t in them. Becomes, for example, some junk times 0, some junk times 0 squared, and so on. So all the rest of the stuff goes to 0. And we get f double prime at 0 equals 2 times c2. And this we defined as acceleration, right? So we get c2
So C2 is 1/2 A.
Right, it's 1/2 a.
Yeah, and that's where the kinematic equate. That's so
Yeah.
cool.
Yeah, so you get xi. Right, you might be wondering, sometimes they'll say delta x equals vi plus 1/2 at squared. The reason why is this is final position, right? So we define this position function as final position in the first place. So this is xf technically. And when you subtract over the xi, you'll get delta x equals vit plus 1/2 at squared, right? So you might be wondering where the rest of the terms go, right? Because you could keep going. So this is vit plus 1/2 a, which is c2 times t squared, c2 t2. Now the rest of the terms are simple, n greater than 3, right? Of cn t to the n. We now know that f of t is equal to this, right? And we know that all the rest of the derivatives are 0, right? So what this means is you're going to have, you can see the pattern, right? So what's going to happen is you're going to have some terms, or rather you're going to have some constants jump down from the exponent of the derivative. Namely, it's going to be the derivative factorial, right? Because you have, 3 jumps down, then it's 2, then it's 1, and after 1 jumps down, then it's 0, right? So you have, for example, 3 factorial times c3. At that point, it has no t dependence. So when you plug in 0, the rest of the terms go to 0. Same idea as with the Taylor series. So you can see that it's just going to be some constant, no matter what that is, times Cn in general, right? So if you have some constant times Cn, and you have to set that equal to 0, well, obviously, you either can have 2 choices, right? You either have, like, for example, 6, or you have Cn, right? And obviously, we know 6 doesn't equal 0. So therefore, we must conclude that Cn for n greater than 3, or greater than or equal to 3, is 0. So this entire thing vanishes. It's just 0 plus 0 plus 0 plus 0 an infinite number of times. And therefore, we have the following equation. And of course, you could keep going, right? You could say, okay, well, let's define f triple prime to be a constant jerk. And then you would get plus 1/6 j times t squared. Right?
And if I had a constant jounce, it would be 1/24 jounce t cubed.
Right, yeah. So that's where the kinematic equation. Sorry if it's a little bit.
So it's just a Taylor series. That's crazy.
Yeah, it is. All right. So that's This is actually done with a lot of things in physics, just assuming it can be written as a power series. By the way, this power series is not necessarily always a Taylor series. Like, people will assume it's a power series, but that power series doesn't necessarily need to be a Taylor series. In this case, it turned out to be a Taylor series, but it doesn't always have to be. Okay, now let's see, view, zoom out, right? So I hope you understood this thing about kinematics. So that's where all the kinematic equations go. Next is Newton's laws, right? And I'm going to take a little bit more of a conceptual approach to this. So I hope you can see my motivations, right? So Newton's first law. Oh, God. Newton's first law, right? Newton's first law is, rest stays at rest. Right, rest equals, and motion equals motion. God, I can't. But yeah, rest equals rest, motion equals motion. The verbal form of it is all objects at rest tend to stay at rest, and all objects in motion in a straight line tend to stay. Very well known. And now we're going to skip to 3, which is simply saying that actions have an equal and opposite reaction. Right? Action equals reaction. Okay. Now, what is Newton's second law, right? So the Newton's second law is probably the most critical one, right? It's how we determine whether things are, kind of getting pushed or pulled, right? So using these first 2 laws, we can actually, and specifically the first one, right? This first one is important, right? So you're probably used to Newton's second law as F equals ma, right? But this is actually not how it is in original form. And the reason is this is actually quite unintuitive, right? Where is the acceleration coming from? Where is the mass coming from? It doesn't quite make sense. And in fact, this is less general than the form I'm about to show you, right? So rest equals rest, motion equals motion, right? So it describes something that's being accelerated, or rather it's having its path changed, right? It would make sense that that object is experiencing something called a force, right? And how do you define a force? Well, a force is anything that knocks that object off of rest equals rest and motion equals motion, right? So F is rather some change in, F is equal to change in some quantity of motion, right? I'll write it as motion. Motion. I don't know how to spell motion. Over time. Right. Why over time? The reason is, well, the more the motion is being changed, you want F to be proportional to that, right? It would make sense if car is turning on a very slight degree versus whether a car is, taking a hard left. It would make more sense for the force to be more. So that's why we introduced this factor of delta T, right? Well, what is this quantity of motion? We define the quantity of motion, right? And that's actually the word first used. He defined it, he said the quantity of motion. It's now something we call, right? So rather, you take the limit as this goes to 0, and you say F equals dp dt, right? And the reason why this makes more sense, well, a force changes an object, right? This is literally just saying we're looking at how much the object is moving. It's mass times its velocity. It's really a measure of how the object is moving, right? It's a measure of motion. That's what momentum is, right? And then we're taking its derivative with respect to time. We're seeing how it changes. That is by definition, right? So this is where the rocket equation comes from, right? Now let me see. Let me pull out my notes and see if I can show you how you derive the rocket equation. Hang on. All right, I have them here.
What's the rocket equation?
I think it's called the Tchaikovsky rocket equation. Basically, it's describing how objects which expel mass move in space, right? So basically, objects with changing mass. In general, any object with changing mass can be modeled as a rocket. So what you have to do is a little bit tricky. You can't apply this directly, right? You could write the momentum and then immediately take a derivative and try, right? Like you could say m of t times v of t, because both of these are changing in time, and try and use the chain rule, right? But that actually doesn't work. The reason why is because these two are not independent. The reason why they're not independent is because the change in velocity is directly linked to how much mass you're expelling. So you can't just naively take a chain rule derivative here. What you have to do is you have to take the momentum of the system at time t and p plus delta t. Right? Now, let me show you what I mean. What is the momentum of a rocket system at p equals? Right. First of all, let me draw you a model. Right. The rocket is like this. There's some hull of the rocket. It can, for example, small mass of fuel, delta m. That's what it looks like. You are sitting here, and it's moving at some speed v. Right? Now, you observe the fuel being shot out at speed u. This is the exhaust velocity. Right? So we haven't shot out the fuel yet, right? So we're assuming it's kind of, at an instantaneous moment in time, you have a delta of mass of fuel, delta that's about to be shot out the end of the rocket. And the rocket is moving at some speed v, right? Now, the momentum of the system is what, right? Oh, by the way, the rocket has mass, capital, right? So, well, it's just the total mass of the rocket times the, right? Momentum is simply equal to mass times the. So it's simply m plus delta m times little v. This is the momentum of the system at time t. Now at time t plus delta t, the momentum of the system becomes, well, let's draw it, right? You have the mass delta m expelled from the rocket, which is mass m. V plus delta v. Now here's the question, what speed is the fuel moving at?
U plus we, no.
U plus v. That's what you said?
Yeah.
Now, hang on. Be very careful. This is tricky because you have to. No, you have to. This is very tricky because you have to analyze it from the frame of a person at rest, right? And from a rocket, right? So listen, right? You observe the fuel moving away from you at u, right? That means been accelerated by plus delta v, you still see it shooting out at speed u. So, but from someone at rest, this is just your speed plus the speed you see it moving. So rather, it's the speed of this delta m is not u plus v delta v. It's u plus v plus delta v. Right? I hope you can see. Yeah, because you see it moving.
I still conserve some momentum.
But you're moving at v plus delta v. So from a person at rest, it looks like simply u plus your own speed. But your own speed is no longer v, it's v. So this is the speed of the mass after time. Right? So now we have p plus delta. This is the state of the rocket after time delta t has elapsed. Is simply this times delta m. V. Again, the normal rules of calculating momentum apply. It's simply the velocity of the delta m mass of fuel times the velocity of the mass times the velocity of the mass times, right? A little bit redundant, but there it is. And then m times v plus delta v. Now it's really quite simple. We just take, as you know, in a traditional derivative, you just say, f of x plus h minus f of x. Well, this is the same thing, except the variable is no longer x, it's t, right? So this would be the same thing as x plus delta x, right? That's what h is when you're taking a traditional derivative. So we can do that here. We just have to subtract these two off and then divide by delta t. Then take the limit as t, right? So first let's distribute this. I'm going to do this very fast if you're having trouble following the algebra. The reason why I'm doing this fast is because writing in MS Paint is a pain, and I don't want to simplify. I don't want to write everything down and then try and simplify, right? So let's see. Times u, or sorry, delta m times u, right? We don't see a delta m times u over here, so we can just simply write delta m u, right? Delta m times v. Well, there is a delta m times v when we're subtracting off, right? So we don't write that term. Delta m times delta v, there's no delta m times delta v over here, so we can write that down. Times delta v.
Since momentum is conserved, shouldn't the two quantities, p of t and p of t plus delta t, be equal?
I think
Is nothing changed in the system, right? So it seems like momentum would still have to be conserved.
yeah, it's an interesting question. I think momentum is conserved here. Hang on. Yeah, we're setting this equal to 0. Sorry, I should say that right up front. This difference is equal to...
Okay, yeah, that makes sense because it's conserved. So
Yeah.
the difference.
Yeah, sorry, I just had I blanked out there. Yeah, all right. So we've already distributed to all these terms. Now we can do these terms. M times v. Well, there's an m times v over here. So we don't write that term down. Now we have an m times delta v. There's no m times delta v. So we can write just plus m times delta v. Right? Very nice. This whole thing is equal to 0. Rather, its momentum is conserved, but there is really we should set it equal to the external force on the object, right? Because we're assuming that this rocket is floating in free space, right? But in reality, there might be some forces affecting it, like gravity. So yeah, it is 0 in this model, but you're not going to have 0 force. So now we divide everything by delta t. You get delta m over delta t. Or rather, I'll just divide by delta t and take the limit at the same time. So what we'll have is we'll have dm dt times u. And I'll skip this term for now, plus m times dv dt, right? And why did I skip this term? Well, we'll have delta m over delta t times delta v, right? So really, if you differentials, you'd have dm times dv, but dv is arbitrarily small, so this term goes to 0. I hope you can see, right? It's a multiplication of two arbitrarily small quantities. You only divide by delta t, so really this term goes to 0, right? And you arrive at this, right? M dv t plus dm
Wait,
dt. Yeah.
how come with big M delta V, it was dV over dt, but with delta M delta V, the delta V just goes to 0.
Oh, so I'll write the step out, right? So right before we take the limit divided by delta t, we observe delta m delta v over delta t. Now the problem with this, right, is when we let t go to, we have a choice, right? There aren't two delta t's to go around, right? So one of these becomes a derivative, the other just becomes a differential, right? So you have dm dt times dv, or you have dv dt times dm. That's the only, you don't have t squared, right? So it's not times it's not a multiplication of two derivatives, right? And the reason why these go to 0 is because differentials are arbitrarily small, right? So technically you could include this because you're never going to deal with real differentials in life, right? So you could include this term, but it's just going to be so small that you just don't include it.
It's arbitrarily small. And it doesn't matter which one you pick because just go to 0, canceling out the dv over dt in that case.
Yeah.
Okay, that makes much more sense.
To arrive here, and this form it's nice, but the problem is we have dm dt. Dv dt we know just represents the rate of change of velocity of the rocket, right? Very nice. Mass is the initial mass, or rather this mass of the rocket. U is the exhaust velocity. That's very nice. We know we can figure out all this very easily. But what's dm dt? Dm dt is the rate at which mass added to the exhaust. I hope you can see this, right? Because we're spitting out, right? So rather, there's some mass m of t of the rocket, but there's also a mass little m of t of the exhaust, right? So dm dt actually represents, we're adding mass to the exhaust, right? And it doesn't really make sense. I hope you can that dm dt represents you're adding mass to the mass of the exhaust.
Yeah, makes sense.
But that doesn't really make sense. We can't really measure that. So we can leverage conservation of mass. If the mass of the exhaust is increasing by dm dt, the mass of the rocket is decreasing by that same amount. So it's just dt times u. And this is the equation that this equals the net force on the rocket. Or in the presence of no forces, where momentum is conserved, 0, right? So I hope you can see that step, right? The mass of the exhaust.
That makes sense.
Okay. And that's the rocket equation. You could also do a lot of things with fluid flow. You could say.
Now, one thing that I'm a little bit confused about is why we set this equal to the force on it, right? So the net force on the system is going to be equal to, in this case, right, it's 0, but it's going to be equal to the change in momentum over time. Why wouldn't change in momentum... Wait a second. Change in momentum over... Oh, no, it actually does make sense because change in momentum, right, is impulse. And impulse is ft, so change in momentum over time is going to be ft divided by t, which is f.
Yeah, right. And Newton did originally use impulse when he was coming up with force. Okay. So I could move on to fluid flow, but I feel like this is rather... so I'll just skip fluid flow. Basically, it was deriving the force on an object. If you're spraying, for example, a water hose at a wall, you can derive how much force is on the wall by a simple calculation. You just say, all right, well, let's assume it's not a stream. Let's assume it's made up of finite particles with mass m, and they're uniform. And they're moving all at a velocity, the velocity of the stream, right? They're all moving at mv, right? So finite particles, equally spaced out. This is the distance L, with momentum. P equals m mv naught, right? This is momentum of the stream. And what you could do is you could find the density, right? This is simply m over L, and multiply this out, or sorry, rather rather this distance should be called big L, right? And the distance between the particles is little l. And you can find the number of particles, multiply it by the momentum, and then divide by time, and you'll get an equation for fluid flow. But I'll leave that as an exercise to you. I don't think it's really that interesting. What is interesting is the actual relationship between force and energy, right? So, all right, hang on, zoom in. Okay. What is interesting is the relationship between force and energy, right? So how do we define work, right? Work is something, it's an entirely new concept, right? So I'll explain it like this. Right? Let's say we have we have an asteroid, right? Now we know how to describe, for example, let's say we shoot a projectile at the asteroid, moving at some speed v, and it impacts the projectile, and all the it explodes, right? So all of the fragments of the explosion go everywhere, right? Obviously, momentum is conserved here, so you would see a net velocity equal to, for example, an inelastic collision of all of these particles. But that's besides the point, right? We could describe this using a coordinate, for example, right? And describing the vectors of each and every single particle as they come in and after they shatter, right? But there should be this is going to sound a little bit stupid at first, but there's something kind of missing here, right? You're obfuscating the real picture, right? It's not really about where all of these particles are going. There's something else underlying this, right? Which is the idea of how big the explosion is, right? How big is the explosion? That doesn't require a coordinate system. That doesn't require vectors, right? So for that, we define the things like energy and work, right? It's simply how energetic this explosion is. So rather than using forces, we can describe it using energy and work. Right? So we define work as force times distance. Some force applied over a certain distance is work, right? And for a particle moving, in the absence of any, kind of field, like if it's not attached to a spring, for example, or in a gravitational field, this is simply equal to the change in kinetic energy of the object, right? You apply a force over a distance, it's going to change how fast the object is moving. That's simply what this says, right? Now,
I have a question about the definition of work, right?
yeah.
So like sometimes work is defined as force times displacement instead of distance, and sometimes it's defined as distance, right? So why is that the case?
Why is it the case that okay, I see what you're saying. So you're saying force times, okay, that's actually a very good question. And the reason for it has to do with how we calculate things like potential energy, right? So the reason why we don't always say distance, and sometimes we say displacement, you're actually right. Technically, it is not distance, it is displacement. The reason for that is if you're moving a certain distance, right? Let's say you move X meters, and then you move back another Y meters, right? The total work done is simply the displacement X minus Y, right? This is the only thing you need to calculate this distance and done from this distance, right? So really it is the displacement. It's not the distance. The reason for it, again, stated more succinctly, is we only care about the net change. Right? But do you understand?
Yeah.
Okay. Okay, hang on. But the problem with this is that this is inherently limited, right? Because we can only deal with constant forces over some distance, right? And that's not always what's going to happen, right? For example, if you throw an object into a whirlpool, the force at every point is going to be different, and you're not going to travel a real distance, right? You're not going to travel a linear distance. So what you have to use calculus, right? So you can extend this definition again to something called line integrals. I don't know if you're familiar with them, but essentially you just say, give me a force field, literally a field. So assigning a vector to every point in space, and that vector represents force. For example, on a two-dimensional plane. Now multiply that by a small change in position and integrate over a curve, right? R hat is simply the projectile, or R vector is simply the path of the particle, right? Now, the problem with this is that you can't actually do fxy times dr. This is just simply a more succinct way of saying, all right, give me a path, right? Give me a parameterization of a path, parameterized by t, for example, x of t times I hat plus y of t times this. This represents time, right? Or rather, it represents position vector. It represents position. It is a position vector, so it depends on only one. Another thing you could say is, well, you can only move in one direction along the line. Well, technically two. You could also move in the other direction. You can only take a derivative with respect to one coordinate, right? You can only go in this direction or this direction. One derivative exists, one tangent line. So you can only take a derivative with respect to one variable, and therefore the function can only depend on one variable. So instead of this, right, this is a little bit obfuscated. Really what we do is we say f of xy, we multiply this, or sorry, we dot this with the derivative of the position vector, and then we multiply by dt. And this curve, we now go from a to b. So once we do this dot product, we recover a scalar, and we can integrate that scalar. Right? I hope that makes sense. This is simply extending this definition. Oh, by the way, this is all equal to work. We define work as this over a general path, and having a general and of course
I personally don't understand, right? But like, yeah, this I probably will have to look into this, but that's just because of my lack of knowledge of this math concept. But
yeah, essentially I can explain it to you the same way as single variable calc, right? You just you take a small segment of the path and you multiply it by the force, or rather you dot it with the force at that position, right? Because this work is not simply force times displacement. It's force times displacement times cosine theta, right? You remember that?
yeah, so I've seen the formal definition of work, right, as the integral of the force vector, right, times the dot product of some instantaneous change in x.
Yeah. It's just saying move the object a small amount and then multiply it by the force at the point that you started at and see how much work is done. Then add it up over the entire path. In practice, you're gonna have f of xy. Or rather, it's gonna be like, for example, x squared times I hat plus y squared times j hat. So this is simply going to assign a vector to every xy. Encounter contradictions and weird things start happening when you start dealing with like electric forces that you have to get around with things like the Dirac delta function. But for this, you don't really need to worry about that, right? So it's saying if you add up the work around a closed path, right, and you have some force field, you take a path that's closed and you add up all the work, right, and you get zero, right? What this means is that the force is something called conservative. What it means is that when you pull it in a full circle, you haven't done any work. So work, how do I say this? This essentially means that energy is conservative, right? Which might seem like a little bit of a jump. But what this is saying is if you go in a full circle, only the endpoints matter. God.
Well, you could just use the work energy theorem, right? Work is a change in energy. If the change in energy is zero, right, then energy is conserved.
Yeah. What I'm trying to communicate is the idea that this is. I don't know. I hope you just take it as a given, right? Like, if you pull an object around a closed path, right, and the work is zero, then energy is conserved in that field. Right? I would have to think about a way to phrase it better. I don't really know that. So what this means is this implies that the only thing that matters in the field is the initial starting point and the ending, right? So that's the only thing that matters for work, is the starting point and the ending point. The path you took doesn't matter. This is an answer. God. The reason this implies that is if you have a closed line integral, right? God, I have to use Green's theorem here. Basically, a closed line integral, right? That's what this is. If you're integrating over a path like this, is a line integral. A closed line integral equaling zero means that some property of the function, a differential operator on it called the curl, is simply another type of derivative, is also zero, right? So what does that mean? Well, if you take a double integral, right, of how swirly a field is inside of a region, let's say a field swirls kind of like this. Now, the field doesn't really have closed lines. Imagine like vectors pointing in these directions that kind of swirl like that. If you add up all of the swirliness inside of a region, this is somewhat, in a sense, equal to, you can see how it's related to if I just walk along this path and find the work along it, right? Because if the force curls a lot, right, or rather it swirls around a lot, the work is going to be positive, right? Because the force is now swirling around with the boundary of the surface, or rather of the shape, right? So it's swirling along with the shape, and therefore when we try and calculate the work around it, the force is generally in the same displacement, and this is positive, right? And that has to do with swirliness, because if you add up all the swirliness on the inside of this region, you arrive at the fact that how swirly this is inside is directly proportional to how much work is going to be done on the outside. God. Yeah, this section really requires a lot of knowledge of multivariable calculus. So, I mean, I could just skip this because not much of what I'm going to, like, a lot of what I'm going to say is just going to go over your head. So, I'll skip this section just because if you don't know multivariable calculus, it's not going to mean anything. And then, it's just a waste of everyone's time. But basically, what you arrive at is that any force that's conservative can have a potential written, can be written in terms of the gradient of a potential. That F equals negative dV dt, right? And this makes sense, right? You want the force is directed in the direction. The force is directed in the direction where you are. Sorry, this is not dV dt. This is rather dV dx, right? Because this is in space, not in time. dV dx. The force is simply, let's say the potential energy is increased, right? Well, nature wants to minimize potential energy. So the force is simply proportional to how much potential energy you have and directed along the opposite direction, right? So you can kind of see where this comes from, right? This is also where terms like potential well come in, right? So force is, again, the derivative of the potential energy function. In space.
Wait, force is a derivative of potential energy?
The negative derivative of potential energy.
Whoa.
I
Okay, I
hope that
didn't
makes sense
understand how we got
physically.
to that, but I don't know. Is it easy to explain with Calc 1 and Calc 2 maybe, or do you need to go into like a higher
In
level?
general, I think I would have to go to prove it generally. I would have to agree, but let me see if I can't do it with actually. Yeah, no, I think I have to use Calc 3 because what it relies on is there's a really nice God, what's the word for it? Cyclic nature, right? And it's referenced a lot in like even higher things like tensors. Basically the gradient, or sorry, these are all differential operators. If you take this differential operator and then you apply another differential operator to it. Hang on, did I do this in the right order? No, I didn't. Hang on. It's the other way around, right? So basically, applying differential operator number to to a scalar, right? This differential operator tells you how fast the function is increasing and which direction to go to increase the function fast. And if you apply another differential operator telling you how curly, this is always zero. Of course, there are some limitations. It has to be. I think some of the limitations are like it has to be continuous and differentiable, obviously, because these are differential. And there are other identities also, right? So if you take how much this is, by the way, this is something called divergence. It measures exactly that. If you have like a lot of fields emanating from a point, this divergence is again positive, right? There's a lot of fields diverging from that point. If they're all pointing in, it's negative divergence, right? These are, again, just all differential operators that can be defined in terms of partial derivatives that I don't care to go into. It would take way too much time. But basically what happens is you measure the curliness of this, right? This is actually the equation, right? Because if f is nice, if it's continuous and differentiable, which is true for most potential energy functions, you can extract. What happens is, remember how I said the curl of f rather is 0, right? And this was the same thing as saying adding up everything, like adding up the stuff on the boundary was 0. This is what we arrived at. Basically, what happens is now we can say f, or rather, I should write this as u to avoid confusion. Now we know the curl of f is 0. So applying this differential operator gives you 0. So f must be able to be written as the divergence of some other function, right? Because the curl of the divergence of some function gives you 0, and the curl of f gives you 0. So f must be able to be written as in this form, right? And this divergence is the same thing as in one dimension, it simply reduces the derivative. So you get dvdx, rather, right? And you might be saying, where's the minus sign? Well, the thing is, we introduced the minus sign arbitrarily, right? You don't need to introduce the minus sign, but what you have to do is you have to redefine potential energy to be negative in order for that to work then. Because if you don't, then you're saying force is directed in the direction of increasing potential energy, which doesn't make sense unless your potential energy is negative. So if you want potential energy to be positive, force has to be directed in the negative direction of potential energy. So yeah, going into multivariable, and again, this probably meant nothing to you, but yeah, it's a really interesting idea, and it should be quite intuitive.
It looks cool.
Yeah,
I didn't understand most of it, but now I want to learn.
Yeah. So the last topic, which is this one is just a lot of just laborious work. Right. So this kind of gets to the heart of what acceleration and those acceleration and God, I'm blanking. Acceleration and velocity and all of these kinematic quantities. What do they mean, right? So what this is saying, what they say, right, is if you have some position vector function r, and you take its first derivative. This is equal to some velocity function, usually as a function of t. Okay. Do you know what I hat and j hat are? These are simply the unit vectors.
Yeah. So
And the important
how come velocity of t is only in the x direction and not the y direction?
I don't. Oh.
Like, should you have
I didn't
vx of
imply
t and
that.
vy of t?
Yeah. Rather, so you take a full derivative of this, right? It's not. Sorry, I didn't finish right. J hat. Take the full derivative of this. So first of all, we can distribute through addition. But now we have a conundrum because we don't know if we can simply pull the derivative inside, right? It would be really nice if we could, but can you? And the answer is yes, you can, right? Because no matter where you are on the grid, right, I hat and j hat are always the exact same vectors. They always have unit length and they are always pointing in the exact same locations, right? No matter where you are. So they have no dependence on position whatsoever. They have no dependence on time. So therefore you can simply, these are like constants. You can simply pull them inside and you get x prime of t, I hat, plus y prime of t times j hat. And of course, this isn't always the case, right? And again, you can keep doing this and you'll get that acceleration in prime of t times I hat plus y double prime of t times j hat, right? And the reason this works is because I hat and j hat are constant everywhere in space, right? And, Cartesian coordinates are nice, but sometimes you want to use polar coordinates. For example, if there's a satellite orbiting Earth, right? It's a lot more useful to use polar coordinates because, the radial distance is constant and it has constant, God, what's the word? Its tangent is described by e theta. What I mean by e theta is a basis vector pointed along the theta direction, right? So it's obviously circles are really nice and the example we're going to use is orbits. Orbits are really, really nice and cool, right? So so let's think about the basis vector polar coordinates, right? So in polar coordinates, everything changes, right? Because at every point in space, the direction of r dot changes, or r of theta changes, or God, fuck. The direction of the basis vector pointing in the radial direction, right? So what a basis vector does is it points in the fastest way to increase a certain variable, right? So for example, j hat points in the direction of fastest increasing y. Same thing for x hat, right? So r hat points in the direction of fastest increasing r, right? But obviously, the direction of fastest increasing r depends on where you are on the thing, right? So for this point, the direction where you increase your radial distance fastest is this direction. Again, and for here, for example, the direction you increase the radial fastest is not this direction, but it's, again, radially away. It's in that direction, right? So already we have a problem because r of theta, or rather the r hat, the basis vector pointing along r is constantly changing everywhere in space. And the direction where you increase theta, assuming theta is counterclockwise, right, is always going to be, well, first of all, it's going to be perpendicular to r, because everything is circular, right? And the radius is perpendicular to the tangent for circles, right? R of theta is always going to be perpendicular, or rather theta hat is going to be perpendicular to r hat. And it's also going to change every space, for example, right? Just by virtue of it always has to be perpendicular, and r hat's changing, so therefore theta hat has to change, right? So when we have a position vector for, well, even that changes. right? Because what you have is R of t equals what? Well, in this we have I hat times j hat, right? Or plus y hat times j hat. In this, you have just some constant radius that changes in time. So R of t times r hat, which again is also changing in time, right? So this is what you have for a position vector. All this is saying is go along the radial direction, a distance to the radius, right? Go the radius amount of units in the radial direction, and this will describe every point on the grid. And this is what the position vector is, right? So what we have to do is we have to do a lot of sets, right? The reason why is first we would like r hat and theta hat in terms of x hat and y hat. What is r hat, right? So r hat is, well, let's draw a triangle. This is theta. This direction is, of course, I hat. This is x times I hat. This is j hat. This is y times j hat. This direction is r hat. And this direction is r times r hat. All right. Well, we don't actually really care about these unit vectors, right? We only care about the magnitude. For example, x times I hat would be the same thing as something in terms of theta and r that equals x, right? So we just simply have to take the magnitude of this entire triangle. So we end up with a triangle that looks r, y, and x, right? Because we simply want the magnitude so we can stick them in front of I hat, and the magnitude that we can stick in front of j hat, right? And from this, we simply see, well, x is equal to simply r cosine theta, and y is equal to x equals r cosine theta, and y equals r sine theta by simple trigonometry, right? And then we can plug this in, right? So we know r times r hat is simply the case of vector addition, right? So we know r times r hat equals x times I hat plus y times j hat, right? But we've already figured out what x and y are in terms of r and theta, right? So this is equal to I hat times the magnitude of x, which is simply r cosine theta, plus j hat times r sine theta. Now we see a common factor of r, we can simply cancel it, and we get r hat equals I cosine hat, or I times plus j times sine theta. So let me just write that, cosine theta. I plus sine j. Okay, nice. Now, how do we get theta hat? Well, we could go through the process of, trying to construct a perpendicular vector, or we could try and use geometry. But what I would like you to notice here is that if we take the derivative of r hat with respect to theta, how does r hat change with respect to theta, right? So if you look at a curve of constant r, and you're simply changing theta, right? How does r hat change? Well, r hat simply changes by moving in the theta hat direction. Direction simply changes by theta hat. So from this, we know dr hat d theta is equal to theta hat. And we can do the derivative over here. We get negative sine theta times I hat plus cosine theta times j hat. All right, now we have the basis vectors in terms of I hat and j hat, right?
Wait, a question. So actually, I thought, right, that the easiest way to do this would just be to take the derivative, because if you think about it, right, like the the direction of theta hat, right, is going to be perpendicular to it, and the direction of the derivative vector, right, is also going to be perpendicular. So that makes sense, the negative sine theta and the cosine theta for theta hat. But what I don't understand is why theta hat is equal to dr hat over d theta. I didn't understand the reasoning there. Could you
Well, the reason for that, right, is because if you right, how do I say this? It's along a constant r, right? So you're traveling along a circle, right?
Yeah.
This is saying compute the tangent vector with respect to theta. Or rather, we can approach and use delta theta. And this is the new r hat, for example, right? Well, the difference vector between them, right, is simply going to be pointed along this direction. I don't know what this is called, but it's like I hope you can see what I'm drawing, right? It's simply this. Yeah. It's pointed along that direction, right? But if you let delta theta go to 0, right? Direction is simply tangent to the circle. So it's tangent to the circle, and it points in the direction of increasing theta. Right? You see both of those things, right? Because if you increase theta, right, and you subtract off these two vectors, when you're increasing theta, when you're increasing theta, the vector points along theta hat, right? Because what you're doing is you're moving r hat in the direction of theta hat. So when you let the limit of r hat go to 0, right, this vector not only points in the same direction as theta hat, it's also, tangent, right? So that's two reasons. Number one, it's tangent to how you're moving it, right? So that's already a qualification for the derivative. Number two, it points along the direction of theta hat. I hope you can see.
Yeah, I got the first reason. I didn't completely get the second reason, but the first reason, yeah, makes sense. So.
Yeah. Okay. All right. I don't know. Sometimes I come up with justifications myself that don't really make sense to other people.
Yeah, no, I trust that it makes sense. I just am not probably thinking of it the same way you are.
Yeah. So again, we can agree that these are our basis vectors inside of polar coordinates. Right? Now we can start differentiating this bad boy, right? And a lot of very cool things start popping, right? I hope I can delete this and this. So we've derived everything, and I'm just going to erase some of our work that got us there, right? Okay, well, we have this fact in mind. We can also numerically take the derivative of theta hat with respect to theta, right? The derivative of negative sine of theta is a negative cosine theta. The derivative of cosine theta is negative sine theta. So we know the derivative just by doing it numerically, no geometric reasoning. We know that this is simply equal to negative r hat. You see that, right? I just did it numerically. It just took the derivatives. Okay. And the reason why I can pull the derivative inside it is, again, the really good thing about working like this, the Cartesian basis doesn't change anywhere in space. So these are simply constants, and I can pull the derivative in. Okay? So what is velocity in polar coordinates? Right? What is the first derivative with respect to time? Let's not forget what it's with respect to. Right? Well, it's two functions of time, right? And we can simply just use the chain rule here. Well, this is simply r dot dot just means derivative, right? Derivative with respect to time. R dot times R hat. I hope you see that. Times plus R times the derivative of R hat, right? The derivative of R hat with respect to time, right? So let's think about this. The derivative of R hat with respect to theta is theta hat, right? So first I'll write that down, theta hat, right? But our derivative wasn't with respect to theta, it was with respect to time. So by the chain rule, we have to multiply by d theta dt, which is simply, well, you could call it theta dot, which is what I'm going to do. Or more commonly, it's known as, angular speed, right? So you get theta dot, right? This is a whole new notation, but the dot just means derivative with respect to time.
Yeah, it's the fluxion thing, right?
Yeah. Yeah. So what we arrive at is something very interesting. We've rederived, rather I should show this. The velocity of an object, or rather, this is not velocity prime, that would be acceleration. This is simply just velocity. The velocity of an object is simply how fast it's moving in the head direction, plus r times how fast it's moving in this direction, right? That's the velocity of it, right? And if we relabel this as angular speed, you might recognize this equation. This is rw equals v, right? So this is simply how fast it's moving in this direction, plus the linear velocity in the theta direction. I don't know. Have you seen this equation before?
Yeah, with an omega instead of a w.
All right. No need to do me like that.
And they look very similar.
Yeah. So we've re-derived how fast an object is moving in the tangential direction, right? So if it's moving in a circle, right, r dot equals 0. And if it's moving at constant velocity, it's simply r omega equals v, right? How fast it's moving. So we've rederived, velocity, some nice things in polar coordinates. Hang on, I'm just going to go get some water. I'll be back in 30 seconds. Yeah, I'm back. Now, finding acceleration is a pain in the ass, right? Because you now have to take the derivative of this, right? And we already see, well, this term is fine. This is simply a chain rule. This term is a this is a product rule. This term is a triple product, so it's going to be a pain in the ass, right? So I'm going to leave this blank, and let's first take the derivative of the first term, r times r hat, and we're taking its derivative with respect to time. Well, the derivative of r dot with respect to time, so the derivative of r with respect to time, and you take the derivative of that with respect to time, that's simply equal to r double, right? The radial acceleration times r hat, right? Plus r dot times, again, you're taking the derivative of r hat. The derivative of r hat we already calculated over here, right? It's r times theta dot, no, it's not. It's not r times theta dot, right? This extra r came from the product rule. Rather, the derivative of r with respect to theta is theta hat, but then we need to multiply by d theta dt, which is theta dot. So rather, it's multiplying by d theta dt. Then we can freely take dr d theta, which is theta hat. First term, not so bad. The second term is much worse. Taking the derivative with respect to time of now, it's probably better to isolate this term and take its derivative, because we know its derivative is simply going to give us some radial component. So that's what I'm going to do, right? So the derivative of this, right, this junk, r times theta dot, is another product rule, right? So it's r dot times theta dot right? Just take the derivative of this, then add r times the derivative of theta dot, theta double dot. Then we multiply by this term, theta hat. Now it's very easy. We just do r theta dot. Now let's be careful. The derivative of theta hat we calculated was negative r hat, right? But that was with respect to theta, right? So again, we need to multiply by theta dot, and then we can multiply by d theta hat d theta, right? Simply our chain rule.
Wait, what's a product rule for like three factors in a product?
Oh, I didn't memorize it. Sorry, hang on. I didn't memorize it. I simply just did I just did two sorry, if it's FGH, right? And you take its derivative.
Yeah.
Right? What you do is you just assume FG is a, right? So you take FG prime, and then you can apply the product rule because it's the product of only two functions, right? So it's FG prime times FG times H prime, right?
So you can just turn it into two separate product rules.
Yeah, it's just two separate product rules, right?
Someone texting you?
Yeah. I just need to get through this. So, it gets a little bit long, but yeah. So it's just two separate product rules. Now I'm gonna do a bunch of steps at the same time. I'm gonna add these two together, right? So to get our final acceleration, I'm gonna add our like components together. So theta hat components together. We get two r dot theta dot. Hang on, let me handle this. So we just add our like together. This is r dot theta dot, and there's an r dot theta dot here. We can add them. We get two r dot theta dot plus r theta double dot. And again, all of this was in our theta dot component. Now we simply add our r dot or r hat components. So this is r hat times hang on, r double dot minus, right? So there's this minus sign here. R times theta dot, right? So it's minus sign r hat theta dot times theta dot is theta dot squared. So theta dot squared. And this is where the dot notation comes in useful because I don't have to write d divided by d, and the primes don't have to get confused with the square, right? So this is very nice for that reason. All right. Now let's consider, this is the last thing. We're going to consider an object moving in a gravitational field, right? Equals F. And what we're going to rederive is we're going to show that objects move in ellipse or orbits are ellipses, and we're also going to show that equal areas are swept out. So this is, I believe, Kepler's first and second laws. Right. So first step to simplifying this is GMM, right? This doesn't really matter. We can just set it equal to a constant. I hope you agree.
Yeah, that makes sense.
And then we're gonna set it aside for a while, right? So I'm gonna do that preliminary work, and we're gonna come back to it in like 5 minutes. Let me see what I left the sign of mu at. Oh, actually, hang on. Yeah, just set it equal to negative mu. This makes things convenient for us later. Yeah, just trust me on that. Now, F, remember, is directed along what direction? The force of gravity is directed along what direction in terms of polar coordinates?
Wait. Oh, in this case, it would be the the centripetal acceleration. So it would be it would just be inwards, right? It would be towards the origin.
Yep, it would just be r hat, right? So the theta hat component is necessarily 0 because you're not getting accelerated tangentially.
But
It's just
isn't r hat going outward? So wouldn't it be like negative r hat?
Oh yeah, you're right. That is actually correct, right? So the actual force of gravity is gm over r squared times r hat, right? And you put a negative sign out. Thank you. Okay. So this, right, is equal to F. And the negative sign is simply because it's pointing inward. Right? So we've already accounted for that in this equation. I'll put the r hat here for so you don't get confused. Right? So we know the theta hat component has to be 0. So we can actually do that now. R double dot equals 0. Right? Now this looks like a differential equation to me. So first step, I see a theta dot and a theta double dot. That's pretty unnecessary. So I'm just going to relabel theta dot as omega. So we only have a first order equation. Okay? So now we have r times theta plus. I hope you agree with this step, right? I simply reduce the order by setting angular speed equal to the derivative of theta.
Yeah.
Now I'm going to do a lot of stuff at once. I'm going to subtract this over to the other side, and I'm going to divide by r and omega. So we arrive at this. I hope you agree.
Wait, where did you get the v?
Sorry, that's supposed to be an r.
Oh, okay.
Right? And I'm going to skip the integration here. Right? So they might be, oh, integration. Why are you just integrating right away, right? The reason is this is a very familiar form, right? Because this is the derivative of a function over the function, right? That looks like the derivative of ln of r. You understand that, right? Because it's the derivative of ln of r is 1 over r times, by the chain rule, the derivative of r. Same thing here. It's ln of w, right?
Yeah.
And these constants on the outside don't matter. 2 ln of r. I'm just simply carrying through the integration times negative ln of omega, and never forget the plus c. Right? Now raising e to both sides, again, I'm going to do a lot of steps. This is going to become r squared on this side. So e to the ln of r squared becomes r squared. This is going to become ln of 1 over w by log properties times c. Right? So I can pull the c inside. This c is equal to ln of c, and then pulling it inside is c w, right? Very non-formal. I'm assuming a constant,
Yeah,
Basically, the restriction that happens is c cannot be non-negative, which will make a lot of sense because it physically represents something. So you get c over omega, right? And c is greater than 0. Right? And by the way, we're going to have to use this a lot, right? So what do you get? You get r squared theta dot equals a constant. We're going to be using this a lot when we prove orbits are ellipses, right? Now let's think about this, right? Let's multiply both sides by 1/2. So let's see, we have r squared. And I'm going to write the speed like this, delta theta over delta t. Why am I writing it like this? Because the speed, right? I don't want to consider the speed as speed at a point, right? If I was considering speed at a point, I would need the derivative. But right now I want to consider speed over some time interval. So using deltas is absolutely sufficient here. right? So what do we arrive at when we multiply out by delta?
When you use the dots, isn't like that like the same thing, right? Like the um the theta, right, with the dot on it, right? Like that's the first fluxion, right? So that'll be the same thing as the change in theta over the change in t, right?
Yeah, but formally it's a derivative, right? I'm treating this no longer as a derivative, but as some finite delta theta over some finite delta t. And the reason I'm doing that is we're considering the object already having a certain finite distance, a very real finite delta theta, right? So we no longer need theta dot. We don't need a derivative here, because we're considering as the object a finite distance, or rather as a finite delta t expires, right? So no longer speed at a distance. I hope you follow the step, right?
Yeah, I kind of get it. The steps before, right? I was thinking that theta dot meant what you wrote there, but now, okay, I get it now. Yeah.
Okay, all right. Yeah, theta dot just means the actual derivative.
Right, so it's just going to be d theta, right? In a, what notation? Not Newton's notation, the other guy.
Leibniz.
Leibniz, yeah.
Yeah. Right. So what this says is, right, 1/2 r squared delta theta. Have you seen this before?
Yes.
This is the area of a circular sector. Area equals c times delta t, right? And notice, this doesn't have time dependence, right? So what we've concluded is, if you're measuring over finite time intervals, the area does not depend on where the object is, right? It will sweep out a constant area that only depends on time. It doesn't depend on where the object is, right? So the farther away it is, the slower it'll move. But it'll also have a larger distance, right? It'll sweep out a smaller delta theta, but it'll have a larger radius. And therefore the areas are the same.
Oh, so it doesn't matter how big or small r is.
Yep. Have you seen this before? This is a Kepler second
law. I haven't seen it in the form of the second law, but I recognize the equation.
Yeah. Okay. Now we're gonna have to use this a lot, to derive that orbits are ellipses. Okay. Let us start by setting r double dot minus r times theta dot squared equal to the force, right? Now we can omit the r hat because we're simply considering the magnitudes of forces, right? When you're considering magnitudes of vectors, it's sufficient to just set them. Right, so now we have another differential equation. R double dot minus r theta dot squared equals... Nay. Huh? Not now. Can I sit here and do my work? Not now. Just wait like 10 minutes. Why? Because I'm doing something. What? I'm just stay on the side. No, just... Huh? Come back in 10 minutes. Okay. Good thing Death isn't recording this. Okay. So this is equal to mu over r squared. Now we just set u equal to 1 over r. And the reason why we're doing this is it makes our life much easier, right? Because now we can take du d theta, right? Because that's what we want to prove. If we want to prove that orbits are ellipses, we need to show that r... Sorry, I'm going to have to use this space, so let me... If we want to show that orbits are ellipses, right, it's not sufficient to show something in time necessarily, right? We need to show that r of theta is an ellipse, right? Basically, it traces out an ellipse in r theta space. That's what we want to show. I hope you follow.
Yeah.
And the reason is, well, u over equals 1 over r, right? It might not seem like this does anything for us, but what this does is, right, let us actually calculate these derivatives, right? du d theta. It's 1 over r, right? What this does is it allows us to frame our derivatives in terms of r's time derivatives. It allows us to phrase data derivatives in terms of time derivatives, right? So when we take the time derivative of this, right, prime, or we're taking the theta derivative, that's actually important, right? Well, first we take the function derivative with respect to r, right? So now we get negative 1 over r squared. Then normally we would multiply by dr d theta, right? But we don't actually, that's what we want to find. We want to find dr d theta. So rather, we just substitute it by dr dt, which is something that we are given, right? The speed of the object, times dt d theta, right? And let's do a brief aside, right? In single variable calculus, we have this really nice relationship where the derivatives are just reciprocals of each other, right? And what I mean by that is, start with y equals f of x, right? Take the derivative with respect to x. You get dy dx equals f prime, right? Now take the same equation, take a derivative with respect to y, right? dy is 1. This is equal to, well, f of x, right? So it's df dx times dx dy, right? So this is f prime times dx dy. Dx dy, right? So now we arrive at dx dy equals 1 over f prime, right? F prime, of course, we define as dy dx. This is just 1 over dy dx, right? So if it's dx dy, we can simply just, it's the reciprocal. These derivatives are reciprocal, right? This applies only in single variables. You notice this, right? I hope you follow that. Okay. Yeah, sorry. This is so we have negative r dot over, remember, we have r squared, and then this becomes r squared, and this is simply 1 over theta d theta dt, right? This is theta dot, right? Now r squared theta dot is very familiar, right? We concluded that r squared theta dot is equal to c, a constant. So let's substitute that in. R over c, right? And this becomes very useful when we take the second d squared u d theta equals negative r dot c prime simply equal to. Arco, can you turn off your or lower your mic sensitivity, because you're actually. Thank you. Okay. So this is equal to, again, we can change the theta derivative of r into a time derivative. So this becomes r double dot under the condition that we multiply by dt d theta, right? Which is simply the reciprocal of theta dot, right? C times theta dot. Now we can solve for God. Or rather, c theta dot, we actually do have to substitute for c here. So what we do is we say c equals, r squared theta. So this is r squared theta dot squared, right? Now we solve for r double dot. R double dot is simply equal to, now 1 over r is u, right? So r double dot is equal to 1 over u squared. Sorry, this is r squared times theta dot squared. Stick a negative sign out front, multiplied by d. Do you follow this step? I just replaced 1 over r squared with u squared, and then solve for r double dot.
Oh, okay, I see.
That's all I did here, right? And then this side becomes, rather we have to solve for r dot, right? R dot becomes c times, God, I'm blanking. C times yeah, du d theta, and we have to stick a negative sign out front. Du d theta. Right. Now we can plug everything back into the original equation, right? So the original equation was this: r double dot minus r times theta dot squared equals negative mu over r squared, right? So I'm going to plug in for r double dot. R double dot is simply theta squared over u squared, right? D squared u d theta squared. R dot doesn't appear in this equation. It's simply r theta squared, right? But r is 1 over u. So this is theta dot squared over u. This is not an equal sign, by the way. This should be a plus, or sorry, minus this, because there's a minus sign here. This is equal to negative mu, and mu over r squared, right? U is equal to 1 over r, so this is negative mu, u squared. Okay. Now, remember, r squared theta dot equals c, right?
Wait, how did you get mu squared?
Oh, mu u squared. God.
Oh wait, what's u?
Yeah, that's supposed to be u. U squared. Okay. Now, remember that r squared theta dot equals c. Okay? We're going to have to use that a lot here. So first divide. So first we see a negative, right? So let's change those all. Right? So I hope you follow that step. And then we divide by theta dot on all of these. God, where's brushes? Here it is. Okay. You divide by theta dot and all. Okay. And I misplaced my dot. Right. Now let's not forget what u is. U is simply 1 over, right? So this is mu over r squared theta dot, right? R squared theta dot is again just c, right? So this is again mu over c. This is theta dot over u squared, right? U is 1 over r, so this becomes r squared theta dot. So this again becomes c. C du squared d theta squared, second derivative of u with respect to theta, plus, well, we can change this into a something that's conserved, right? As it stands, this is simply r theta dot, right? But what we can do is we can multiply and divide by u. So we have theta dot over u squared times u equals mu over c, right? Theta dot over u squared, well, u squared is simply 1 over r squared. So the compound fraction reduces to r squared theta dot. That's simply c. And we're nearing the conclusion. Squared, theta squared, plus c times u equals mu over c. Now this is very nice. Well, essentially we're done here, right? I could conclude here, but for the sake of finality, let's just go through and solve this. Divide by c and rename mu over c squared equal to k. Was k. So I'm dividing by c and renaming this k. Right? So what do we arrive at? We arrive at du squared, d theta squared, second derivative of u with respect to theta, plus u equals k. Now all we need to do is subtract u on both sides. We get the second derivative of u equals k minus u. Right? Now all we need to do from here is we just say, well, k minus u equals L. Remember, k is just a constant, right? So the second derivative of L with respect to theta, because again, u is a function of theta, therefore L is a function of theta, equals negative du squared d theta. I hope you can see that.
Okay, so
So
why are we just arbitrarily assigning L to K minus U? Like, is this going to be...
this is very useful because, well, technically we have already solved it here, but we're going to recover the simple equation. We get dl squared d theta squared, and I'm going to kick the negative sign over equals negative L. I hope you can see that. This is technically negative L dl squared d theta squared equals L, but I just move the negative over to the other side.
Okay.
And this defines a simple harmonic oscillator. I don't really have it in me to solve this, but basically what you do is you guess e to the at, or e to the kt as a solution. And I'll just go through it for the sake of completeness. You guess that, well, first of all, what do you see? Why are you guessing this solution? Right? You guess this is the solution because you see a second derivative of something is in terms of itself, right? So a function that obeys that property is e to the kt, right? So second derivative of e to the kt is this, right? It's a times e to the kt
K squared.
times k squared equals negative a times e to the kt. Now a times e to the kt is never zero unless a is zero, which is a trivial solution. So we don't really care about that. So we just divide by that, and we get k squared equals negative 1. K equals I. Okay. So we get the solution is in fact a times e to the it. Right? But what happens is this is obviously e to the it is like cosine theta plus I sine theta, but we don't see imaginaries. So we simply say this is equal to cosine. Right? So we omit the sign and we just say it's equal to cosine with a phase shift.
It looks very similar to Euler's formula. It's interesting how we get like a connection with this thing that we did. That's completely
with
different.
orbits. Yeah. Well, there are still a few steps. So we've solved for this. So now we know L is some a times cosine omega t plus the phase shift. Right, so now we know L is equal to a cosine omega t plus some phase shift. Now we can simply go back. L we defined as k minus u. Well, k we defined as mu squared over c. Right. So solving everything at once, we get u equals mu over c squared minus a cosine omega t plus the phase shift, right? All I did is back substitute for u. And now we arrive at, finally, we can plug in u equals 1 over r. Just take the reciprocal of this. We get r equals c squared over mu times, or plus a times c squared cosine omega t. Omega t plus the phase shift, right? And what happens is if you, or rather, this isn't in terms of t. Sorry, I messed up. The differential equation, everything is in terms of theta. So rather, this is omega theta, omega theta, omega theta. Once again, sorry about that. So yeah, so we arrive at an equation for r of theta, and the general form of this is r equals some constant. We just say 1, and we said all constants equal to 1, right? Or 0 in the case of the phase shift. We say this r is equal to 1 over 1 plus cosine theta, and if you plug this into Desmos, you're going to get a, right? And that's it. That's it for the lecture, actually. That's me trying to review basically everything in mechanics at the calculus level.
That's really cool.
Yeah, The funny thing is, I actually didn't figure out how to do this until 5 minutes before the lecture, because it relies very heavily on this fact, right? And this is interesting because if you multiply by 1/2 m on both sides, right? Well, mass is just arbitrary, right? But this is still going to be equal to c, right? Well, 1/2 mr squared, it's a particle, right? It's not like a spinning tube, right? So 1/2 mr squared is the moment of inertia.
Yeah, it's the rotational inertia times the angular velocity.
So this is saying angular momentum is conserved, which makes sense, right?
Oh, and okay. Angular momentum is rotational inertia times angular velocity. I remember that. And that is a constant. Damn.
Yeah, so this is why I hate when people teach classical mechanics without calculus, because it just makes so much more sense with calculus.
Yeah, dude, okay, that is crazy. Using simple calculus, I can prove that angular momentum is conserved. I thought we need to use Noether's theorem or something like that, but this is really simple. I mean, it's not super simple, right? But it's simple enough that I can understand it.
Yeah. You actually can use Noether's theorem, but what you have to do, right, is you have to find the kinetic. I don't know how much you know about Lagrangian mechanics, but it relates back to what I was saying about work and energy. There's just something wrong with the idea that you need a coordinate system, right? Because nature, what Lagrange did is, you might say in a comic sense, is he took to heart the phrase that nature finds a path of least resistance, right? And what he did is, he simply said, okay, assume every particle or the path that every particle takes minimizes something. And he proved that the thing that it minimizes is just the kinetic energy minus the potential energy, right? And I could show it to you, but I'm really tired.
Yeah, that was a lot, but yeah, I understand why you're tired.
Yeah, so he proved that that's the case, right? And then what you do is the kinetic energy and the potential energy of a system, those are just in terms of the free variable system, right? So for example, this would be in terms of r and theta, right? And then all that's left to do is, if you want to prove that angular momentum is conserved, the genius thing about Noether's theorem, and I really like Noether's theorem, Noether's theorem is probably my favorite theorem, right? All you have to do is just say, okay, well, if you rotate how do you say this? If you rotate your coordinate system, right, does the kinetic energy minus the potential energy change? If it doesn't change when you rotate your coordinate system, then angular momentum is conserved. So Noether's theorem at a high level just says every differentiable symmetry of a system corresponds to the conservation of some quantity, right? So if you move forward in time and the Lagrangian isn't changed, or rather the kinetic energy minus the potential energy isn't changed, it's called the Lagrangian, and that doesn't change, then that corresponds to energy conservation, for example, right? So every single transformation that's differentiable, if it doesn't change anything in the Lagrangian, that corresponds to some quantity that's conserved, right? Which is absolutely incredible, because that you can use that to define things that to define new quantities, right? You don't necessarily need to stick to these antiquated notions of momentum and force. Just getting really lucky and lucking onto concepts like the conservation of momentum, the conservation of mass. You can actually use the Lagrangian to derive new quantities that are conserved, and you can use those conserved quantities to solve problems, right? So it's really nice in that way.
So,
but yeah.
Okay. So now that the lecture is over, right? Yeah. Oh shit! I'm getting a call. Give me a sec.
Energy is conserved because work done is forced to play with circular motion.
All right. Okay. So where am I supposed to learn these sorts of like math and physics concepts, right? Without I don't know.
Oh,
Just
okay.
like watching a bunch of lectures. Like, is there like a textbook that I can get online for free? Is there?
Yeah, hang on.
I don't
Let me see if I can just show you my tabs without doxing myself. Yeah, I think it's generally safe. Okay. All right, that's my personal email. Probably shouldn't click on that. All right, here is God. All right, here is a setup that I have. This is a whole bunch of textbooks that I have set up to learn this. Now, sorry, mandatory disclaimer, I didn't actually learn a lot of stuff from these textbooks. I already knew most of it. But this is like very base level, right? This is very entry level mechanics or physics, right? So as I progress, I have more textbooks already lined up to learn from, right? Especially this one. This is like my end goal textbook. This is it's I don't want to say it's way out of my league, but it's basically way out of my league, right? It has the nice thing about classical mechanics is if you go far enough, right? See, and canonical transformations. Where is it? Perturbation theory and continuous systems and fields, right? So this is right. You see right here examples of relativistic field theories, right? So once you go far enough in classical mechanics, this is a classical mechanics textbook, by the way. Once you go far enough in classical mechanics, you'll arrive at things like fields, right? And then you can use that knowledge to you can apply it directly to things like quantum mechanics and field theory, right? So that's a cool thing. As for, I know I just dodged the question. So as for things you can learn from, right? Khan Academy was really, really helpful for me to learn everything up through calc, right? But you already know that, right? So let me think. The actual mechanics stuff. Where did I learn that stuff? Let me think. Let's see. I actually did learn a lot from this book. It's K and K. You can just type K and K. It's David Kleppner and Robert J. Kolenkow, an Introduction to Mechanics. This goes over. I basically pulled directly from this book, especially for the rocket example. Right. This goes through everything: momentum, work and energy, the gradient Stokes theorem right here, rigid body. Non-inertial systems, right? Physics in a rotating coordinate system. Time derivatives. Remember, this is basically what we did. So yeah, this goes over a lot of the stuff I was to you about.
Can I find this for free online, or do I have to like pirate it or something?
Yeah, it's on LibGen. It's a very famous text.
Oh, okay.
I think most of the textbooks I have are pirated. Other than that, Paul's online math notes for multivariable calculus.
Oh yeah, I've seen that.
Let's see. Honestly, I just got a tutor.
Math.lamar.edu. I use it a lot.
Yeah. I will throw out a disclaimer. You can probably go through this and actually learn more, right? You can go through, do the practice problems and the assignment problems, and like actually learn multivariable calculus, right? But I would just recommend, honestly, just getting a tutor. That's what I did because it's a lot to like try and teach yourself like all of multivariable calculus. Really, I don't like how anything is taught in the end, right? But the problem with that is that you have to introduce topics that are really hard. Why am I talking about this now? It's because everything in multivariable is just a special case of things in tensors, right? Everything in tensors is just a special case of like, things in real analysis. And then real analysis is just a special case of topology, right? So you can keep going up and up and up, right? And someone who's, learned more than you can always say, oh, you're not getting the true essence of it, right? And that's why I don't really like how anything is taught, but you have to start somewhere. It's kind of a rant, but
yeah.
So yeah, I'm just gonna stop screen sharing now. I mean, if you have any questions about anything, I'm open. But
All right, I think I got all of that, or most of it. I
Yeah,
didn't
it
get the
was a
part when you
lot.
went into multivariable. Okay, so
Yeah.
I'm supposed to learn multivariable next year on my own, but I'm afraid I'll just be lazy and I won't do it.
Um. Yeah, that's the reason why I got it. Because I've learned that I'm like not very motivated to learn things on myself.
Yeah, like if I were, I'll be, or it's like even with like online courses, right? Like some online courses I've just ended up dropping, not because I'm not even interested in the subject, right? I'm just too lazy to actually do the work.
Yeah, yeah, definitely the deadlines help to motivate you, but like it's not a strong enough motivation unless it's face to face, right? Because what if you forget to log on one day and then yeah, just end up dropping the whole course,
Yeah.
right? But yeah, I basically did this entire lecture. I didn't expect that many people to come. Um, Mainly it was just to go through classical mechanics for anyone who's interested because a lot of people here like I get a lot of questions about resonance and things, and I know I didn't go over that, but I just wanted to give a lecture on basis things in physics, things that I had really strong knowledge in that I thought everybody could benefit from. But yeah, I didn't expect a lot of people to show up. Next time I might do some, at the risk of being pop science and oversimplifying, I might, do some other concepts like general relativity or, quantum mechanics. That quantum mechanics everybody seems interested in, but
Yeah. I mean, there's only one reason, right, why I want to know about quantum mechanics, and it's like the essential question that like is it deterministic or not?
it is
Like,
deterministic
see,
in a
that's
sense.
everybody says something different. Oh my
Well,
god.
in a sense, it's deterministic. Basically, you can determine how the wave function will evolve deterministically, right? That's what I can say. I think if I went beyond that, that would be philosophy. But what I will tell you is that you can describe a quantum state with a wave function, right? And the Schrodinger equation will tell you how the wave function will, right? It will evolve very. If you have the state of the quantum system at one point, you can determine what the state of the quantum system at another point will be. In that sense, it's deterministic. I don't know what definition of deterministic you're using, so I won't say anything more than that. Yeah,
Okay.
yeah. So if that's it, I'm gonna go downstairs if there's anything left because I skipped lunch.
Oh,
Unfortunate, yeah.
yeah. Eat
We
lunch.
had taught today, so oh god, that was such an Anglo pronunciation. Yeah. All right. Yeah. See you.
See ya. The whole thing, like the conservation is what really blew my like. I didn't realize that you could prove that angular momentum was conserved using like single variable calculus.